Hello everyone. Today I will be talking about how to build resilient infrastructure at Uphold. But first of all, let me start with a quick question for you. How many of you have ever been woken up by an incident at the middle of a night? And what was your solution? Turn it on and off again? Restart everything? Sometimes it works. But first of all, let me introduce myself. My name is Diogo Torres. I'm a senior reliability engineer at Uphold. I joined the company back in 2020, right after finishing my master's in informatics and computer science in the University of Porto. At the time, I was looking for a place where I could really learn how to build systems that scale, and Uphold was already dealing with millions of users, exactly the kind of challenge I wanted. Since then, I've worked across multiple teams, helping to build features throughout the platform. And today, my focus, together with my team, is on making sure that our platform continues to evolve to be even more resilient and scalable. And what is Uphold? Uphold is a global multi-asset trading platform with more than 60 million of users. On our platform, you can not just trade crypto, but also fiat currencies and precious metals. We support over 300 different assets, and every month we process billions in transaction volume. That scales brings a lot of opportunities, but also a lot of challenges, especially when markets get volatile. So, on the right, we have our Uphold wallet, one of our main products, where users can buy, sell, and hold crypto. Then we have our enterprise API, which allows partners to integrate directly with our infrastructure. Next, we have Topper, an on-fiat on-ramp solution, Volt. So, as you can see, Uphold is just a single app. It's a whole ecosystem that serves retail users, developers, and enterprise partners. So, how our platform looks like. I will present a very simplified version. So everything starts at Cloudflare, where handles all the incoming traffic, rate limits, routing, and other stuff. Then the traffic goes through Kubernetes. We are running on Amazon AQS. And then for data, we rely basically on RDS and Aurora databases. We have around 35 clusters. And on Elastic Cache, specifically Valky, we have around 15 clusters. So let's take a look into our main production cluster, which contains around 100 namespaces, each one dedicated to a specific project. We are talking about 265 services, 1,000 deployments. That summed up to 3,000 pods and 7,000 containers. The cluster runs on about 66 nodes, consuming roughly 1,400 CPUs and 3 terabytes of RAM. As you can imagine, when market activity spikes and traffic surges, the entire cluster has to scale. So what you're seeing here, this is just our baseline, what normal looks like for a day-to-day operations. I said normal because we usually are 20% overscaled, so we can deal with incoming traffic. So we already looked to our cluster, our platform. So now let's look to some charts, some metrics, and understand better what a normal day looks like. So here, this is a typical week in production. As you can see on the left, we have the Cloudflare requests for the last week. It fluctuates naturally during the week as user activity rises and falls. We can see that the minimum value is around 1 million requests, and the top is 3-4 million. And on the right, we have our P95 API response time. That, as you can see, it's healthy. For us, healthy, it's around 90-100 milliseconds during the day. Let's look to our database now. On the top, we have two charts, master and replica CPU database load. And on the bottom, RDS load. That's because we have our main database running on EC2 machines. So these are different charts for that. and on the left we have client connections waiting related with our database pullers. Nothing extraordinary here. CPU is around 5% on master and replica. RDS load, it's around 15-20%, so everything is healthy, everything is performing well. Finally, let's take a look to our Kubernetes metrics. On the left, we have the CPU spent by our workload nodes. We can see that around 20% of CPU. On the right, we have the HPA replicas, or rated Uphold autoscaler. I can say that the first line, around 140 replicas, it's our API. So we have 140 APIs running most of the time. And on the bottom, we have CPU partial stall, a metric that correlates with how throttled an app can be. So nothing extraordinary, everything looks normal, everything looks okay. But then we have the crypto market volatility. But as you all know, in the crypto world, normal doesn't last very long. It's unpredictable, and what it makes it so challenging. If you think about it, most markets like stocks or commodities, or if you think in a Formula 1 race or a soccer game, it has like a start and an end, and you can roughly predict how much traffic do you have according to the importance of the game or something like that. In crypto, it all depends on news. When something happens, like maybe a major announcement, Donald Trump wins the election, or a regulatory decision, like Ripple wins landmark case against SEC, or even just a tweet from the right person, the markets can go crazy instantly. Here, we have the Bitcoin price since July 2024. We can see an increase in price around November, December 2024. That was when Trump won the elections, and then we can see other fluctuations. So basically, when thousands of users rush to trade at the exact same time, price starts to moving fast, and suddenly every part of the system is under pressure. Here it's another chart related with XRP price. We have already seen Bitcoin, Ethereum, or XRP shoot up like 10% in an hour, and that kind of movement triggers a massive wave of user activity. So now, let's take a look for our platform during the same period of time. Here, as you can see, it's our Cloudflare requests since July 2024 until now. The first month, we can see that the traffic was around 50 million requests. And then after the elections, we can see an increase to 200, 300 million of requests. So that scale, it was like 3-4 times more traffic that we used to in a short period of time. Then it calmed down around January, another spike in February, and another spike in July. So as you can see, our traffic is not consistent during the entire year. It can simply skyrocket in a few minutes. And the one thing we learn over time is that we can't prevent volatility, but we can prepare our system to survive it. So let's focus on one of those moments when Bitcoin hit 100K. This was one of the moments that we'll never forget. Within minutes, trading volume exploded. Everyone wanted to buy or sell, and it exposed our weak points in our platform. Let's go through some charts again. On the left, you can see the traffic from Cloudflare. It was around 3 million, and on December 2 and Tuesday 3, we can see that was around 10-15 million. So it was like 3 or 5 times more than our usual traffic. And then our P95 API response time had a spike. We can see that our normal was 100 milliseconds, and it was like 2 seconds or 3 seconds after that spike. That might not sound catastrophic, but when you multiply that delay by millions of users, trying to trade, it becomes a huge deal. Let's look our Kubernetes cluster look like. On the left, we have the CPU spent by our workload nodes. As you can see, 80–90% during the same period. We can see here our HPA, horizontal parallel scaling, working in the same period. We can see that the blue line scaled until 15 replicas, but we can already spot an issue there. On the yellow line, it has a flat line on the 10 replicas, so we have probably a misconfiguration of this. The cluster needed more replicas, and it maxed out on 10, so we had to increase manually this value. And we only find out after analyzing all the data. And on the bottom, we have CPU partial stall. Most of our applications were having throttle by 100 and 150 milliseconds, and that's a lot. So while the system stayed online, we were right at the edge of our limits. Now, let's look at the database, the more concerning one. Our master and replica did fine, around 15–20% of CPU, but the major concern, it was this one, reaching 80–70% of CPU during that spike. And on the left, we can see a lot of client connection waiting for our database pullers that were stuck. So we had a throttling issue here. Good. So what we learned and how we evolved. After we analyzed all the data, the first thing that we did, it was we created a dedicated reliability team and started a plan to make sure this will never happen again, or at least not in the same way. Before this event, we already had many features in place. We already had Carpenter for node auto scaling. We already had vertical pod auto scaling for most of the applications. We already hit an issue with NES resolution due to a package on Alpine images. We switched everything for Debian-based ones. We already upgraded our Aurora and Valky databases. By upgrade, I mean we are running the latest version. We already had tuning the parameters, and we already were using like the correct machine. Like if the workload needed a R8X large, it's what is provided. We already added index for database and improved client pools. We were using Linkerd for TLS and also to improve our load balancing across gRPC and HTTP services. We improved downtime for our microservice architecture because, as I said before, we are running around 35 databases plus 15 Valkys. So we had to make sure if one of these services went down, it didn't bring down the entire application. And we worked a lot on that end with our API team and our front-end team to make sure that our wallet could resist this kind of downtime. And it also helped to the upgrades so we can easily shut down the services, do some maintenance, and turn it up again without doing a major outage in our application. And in the end, we were aware that Postgres has a fast path cache of max 16 locks. And if we go above this, probably we hit some contention on database. So we try to keep this value monitored. So we already had this, and we saw some issues. So after this incident, we had to look deeper. We started with infrastructure improvements. We thought that here it's where the major gains were. So I will start with a quote. We thought that the database needed more CPU. So we are talking about that database that were around 80–85% of CPU. But the real issue was API throttling cascading into our database pullers. So probably scaling database will be wasted effort and wasted money because the problem wasn't there. So let's talk about contention, the real issue here. We found that the issue wasn't just traffic, it was the contention of the entire system. Even with multiple replicas, our HTTP and RPC servers were CPU throttled, which caused requests to pile up and block database connections. So the database wasn't the bottleneck, it was just collateral damage. To fix that, we implemented a few things. One of them, it was introduce horizontal pod autoscaling with CADA for these workloads. We already had for Cloudflare D and Ingress in Nginx, but we didn't have that for the HTTP and RPC servers. For each one, we dedicated one core per pod a CPU request. That made the trick. We choose one core because most of our code base is Node.js, and since it's single-threaded, theoretically, it can pass the one thread per consumption, so one CPU. So they could process and release connections quickly. We also isolated the critical HTTP and RPC servers into a separate Carpenter node pool. That way, spikes in background jobs or other apps can't impact our core trading system. And we improved observability. That charts that we saw before, CPU stalls, percentage of CPU by our workload nodes, and even the HPA number of replicas, it were metrics that we didn't look at. And now we are looking. And we added distributed tracing to our platform. So, of course, infrastructure alone doesn't solve everything. We also had to look at our application code. And no, it's not that we were writing bad code. It's just that when traffic grows that fast, small inefficiencies suddenly matter a lot more. When we analyzed traces, we found a few issues like unoptimized requests such as non-dedupe RPC calls, slow or excessive number of database queries, slow external calls to external providers, requests that asks for information that is not used at all, doing a select star or select everything on a database. This one, it's like if you only need like 2 fields of a row, and we are asking the entire row, we can imagine that if that 2 fields occupies like 10 bytes, but the entire row it's like 1 kilobyte, if we multiply that for 1 million requests, we can easily saturate the network. We already had that issue before. So to note here is only ask what you need and not everything, because later you can see like network problems. Issue number 1, missing data loaders. For those who don't know, data loaders can have basically 2 functionality, caching or batching. So let's analyze here a trace. Our wallet uses GraphQL API. So here we can see that one request for the GraphQL API made 92 calls to the get account service, 54 calls to the get card, and 46 calls to the get transaction set. If we multiply these by, I don't know, 10 requests, it will be like 540 calls to that services. If we scale more, 1 million, 54 billion of requests just of this unoptimized query. Here we can apply like caching. If, for example, the get card is calling the same service with the same ID, or implement batching. We can, instead of calling the services 54 times, we can aggregate the IDs that are needed and send an array of IDs to the service. And then if the service uses like Postgres behind, it can use a where clause with an array of IDs. So we are talking 1 million requests, 1 million calls to the services, 1 million calls to the database. Let's go to the second issue, obsessed of concurrency. Here you can see a call to get asset market information. At that time, we had 266 assets, and we are asking information to Redis using a get all sequentially. So even if Redis is fast, it was like 1 millisecond for each request. If you do that sequentially, it will take 200 milliseconds. we can easily here replace this by a Redis pipeline and do this in parallel. So instead of 200 milliseconds, it will be like 2 or 3 milliseconds in total, so a lot faster. And let's go for the final issue, excessive database queries. Here you can see a call to our RPC server search transactions. It took around 230 milliseconds, but the more interesting part, it was one call of an RPC made 100 calls to the database. We already had in place things like we have distributed the load between the master and the replica database, but that wasn't enough because we are talking one request to 100 calls to the database, and when we are talking about millions of requests, this is a lot. So after these findings, we held a workshop with the engineering teams to understand the issues and understand the code, because we just analyze metrics and traces. We don't know the code itself, and align on improvements so we don't repeat history. Then we waited until the next spike. And as you know, as crypto markets can go up and down in years or months, we were in November, December 2024, and we had to wait 7 months until a similar spike. We are now in 7 July 2024, 7 months after the last spike. We already implemented a lot of stuff, so Bitcoin hits 120K. This was what we called a crypto week in the US, with new legislation being discussed at White House, and this was our redemption arc. What almost broke in the past now held strong. So let's look at some metrics now. Here we have the Cloudflare requests on the left. In November we saw 10 million of requests during like 2 or 3 days, but here we can see a similar spike between Friday and Saturday of 15 million requests, so we can compare the two data points. And here, our P95 API response time. From Friday to Saturday, we saw a small spike to 200 milliseconds, but after that it stabilized. It was when our HPA kicked in, so it increased the number of replicas of our deployments, services, and the platform went through. So no major degradations, no service outages, just consistent performance. Compared to the December event, this was a massive win for us. Now let's take a look to our Kubernetes performance. So on the left, once again, we saw an increase to 40% of our workload nodes, nothing compared to 90%. On the bottom, we see partial stall, 40-60 milliseconds, nothing compared to 200 that we saw before. We had like most of our applications were throttling. Now it's just 1 or 2. And on the right, HPA replicas, horizontal pod autoscaler. It scaled when it needed, and then it scaled back. So the cluster was scaling smooth. And let's look to our database load. With a similar spike, we are talking about 15 million requests at peak. From Friday to Saturday, our master database didn't even notice it, probably 10% of CPU. Our client connections waiting before was like 100, 200. Now we are seeing 0.01, so an healthy value. And that blue line, that was the other database that reached like 60, 70, 80% of CPU without any upgrade of hardware, now reaching 30 CPU. So this was large thankfully to the resource tuning, giving one dedicated CPU for each server made the trick. And that's it. I want to finish with this sentence. This sentence is written by me with help of ChatGPT. Resilience is not about avoiding failure. It's about recovering fast and earning trust. We learn more from failure than from success. So failure, it's a nice thing to hit. But the second part, it's the more important one for us. We are dealing with real money. We are a fintech. We are dealing with customers that trust us, and they want to see that their money is secure. When there is a spike, they wanted to trade. And if the platform goes down, they can't see if their money is secure, if they then can sell or buy more crypto. So I remember that in the past, we had issues that we took like an entire afternoon to recover. Only on the night we bring our application up. We lost a lot of money. We lost customers because they don't trust us anymore. And nowadays, I remember one or two issues. Probably we were down like for 10 minutes or something. The worst issue that I saw in a few months from now behind it was like we went slow for 1 hour or something. We didn't went totally down, so customers could see their balance and their money was set. Thank you.